Welcome. Linking structured data to unstructured data, bringing together two industry-leading technologies to improve future decisions. This talk is a collaborative effort focused on addressing a common industry problem. Our presentation has 4 parts: an overview of the challenge, tackling structured data, tackling unstructured data, and a use case where we will link the structured data to the unstructured data. What is the challenge that we're trying to address? I'm sure you're familiar with the challenges. However, I highlight a few common challenges that we have observed that you may have experienced. There has been many years of interpretation and analysis, following IT systems upgrades, constantly evolving file formats, and an increased capacity to store more information. Together with mergers and restructuring, we now have unmanageable volumes of data, and there is a risk of critical knowledge being isolated or lost forever. Therefore, the challenge for data managers and geoscientists when working on projects is to be able to quickly find trusted information, to better understand what data exists and its availability, to know if we have duplicates that we can remove to help improve the company's data resource, and crucially, to implement a system that does all of the above while reducing the need for people to manually review each record. There are 2 parts to this challenge. Over many years, we now have countless EMP projects generated by a variety of software containing what we refer to as structured data. In addition, there's a multitude of files, Excel files, PowerPoint presentations, PDF reports, and scanned images, which we refer to as unstructured data, distributed across on-premise file systems as well as hosted on the cloud. For structured data, application connectors can be designed to help locate projects and extract relevant metadata, over which analysis and subsequent preparation of the extracted metadata can be carried out. For the unstructured data, the use of intelligent search and the extraction of text, including use of OCR on scanned images, enables classification and categorization of the data. Once the metadata has been extracted and the classification and categorization complete, the products from both stages is combined to provide management and users with detailed insight from which strategic decisions can then be made. We shall now look at how we tackle the structured data.
Managing structured data poses several challenges, with a large variety of software applications from multiple vendors. Interica OneView has workflows and connectors that can scan multiple applications and projects from a variety of vendors across Windows and Linux platforms. This could be Patrol, Recall, R5000, or Geolog, for example. So as data managers, what can we achieve? Knowledge of the data landscape allows decisions to be made on data migration, archiving, deleting, and identifying data quality concerns. The ability to view data across multiple projects and applications using key identifiers provide rich metadata and statistics about the project. Projects that meet predefined criteria can be automatically selected for archive or cleanup and move into, for example, the OSDU. This is a typical EMP project structure with wells, 2 and 3D surveys, horizons, and associated project files. Here we have an example of connectivity and results in Interica OneView. On the left you'll see a list of applications that are connected. In this case it's scanning projects in Techlog, Patrol and Paleoscan. The filter is wells, and to the right you'll see a list of well names and UWIs, and then a map display of the locations. This is relatively simple looking, but there's a lot going on in the background. The application could be scanning terabytes of data to achieve the results, providing a detailed look into the projects without the need to open the applications. Here we have an application summary chart. This is showing the percentage of disk space in use and by which applications. This identifies quick wins as far as disk management. This chart is identifying old, large projects. In this example, the highlighted area is showing a 15-year-old live Patrol project containing 12 gigabytes of data. This would certainly be a candidate for further investigation and possible archiving. So with the extended metadata collected, analysis of the project and data duplication can now be completed. The next step is to export the metadata as a CSV file. The file is then ingested by Petrosys software for comparison and analysis against the unstructured data. We're looking at incorporating some future automation into this step via an API. Paul will now go through the unstructured data crawling and analysis.
I'm sure I'm not telling you anything new, but the challenge itself comprises unstructured data such as well reports, seismic acquisition and processing documentation, in-house or external evaluations and analysis, commercial reports, presentations, and much more. In many companies, this can present a sizable challenge. Exploration teams can hold many tens of millions of files in various formats across many different folders where ownership and access is complex, and a significant proportion of the data comprises duplicates or working and final versions, and the creator, the owner of the data, may have long since left the company, so there's no one to ask about the quality of the information. What kind of tool is Elasticsearch? It's a complementary tool intended to work with some of the solutions that you may already have in-house. It's not a replacement for SQL or Oracle, but it's specifically designed to do fast search of large data sets, be it structured or unstructured text, numerical data, or geospatial data. It is written without the traditional burdens of relational databases. Elasticsearch is fast and scalable, running across multiple machines on multiple nodes, and it can solve small or very large data management challenges. There are 3 stages to the workflow we will present, but in summary, and in Elastic's own words, Elasticsearch is where the indexing, search, and analysis magic happens. Broadly speaking, step 1 is to locate the data on the various devices, drives, and data stores, and to make it available to Elasticsearch in a compatible format. Step 2 is where the indexing, search, and analysis magic happens, where it is also possible for data managers to continuously improve the model used for classification and categorization. And step 3 is where the results can be displayed, the information analyzed providing a platform for user access or for further work to remove duplicates and verify the quality of information that is being catalogued. As a part of the intelligent search process, we've developed a crawler to find data, turn it into a series of records, to map data types to an object, extract the content of the files, and push this information into Elasticsearch. The purpose of the intelligent search step, step 1, is to derive better search results from the various data sources and to see a breakdown of document types, which also intelligently takes advantage of the contents contained in various records. Subsequent to the classification and categorization of the data, and to aid analysis, we've also configured solutions to read the indexed information and to display it using a variety of visualization tools, step 3. This is better illustrated in the following slides. In step 1, we read the data from various data sources. We then transform the data into common objects over which we will scan the content and convert the data into a compatible output format for Elasticsearch. In step 2, Elasticsearch will then be used to work through the data provided and begin classification and categorization of the documents. And at this stage, data managers will be working to improve the data model so that subsequent iterations of the workflow improve the classification and categorization results. In step 3, which will often be run concurrently with step 2, the results of classification and categorization of the data can be viewed in a records management tool and can help inform the continuing development of the data model. If we take a closer look at the interactive improvement of the data model, we are essentially aiming to identify documents which represent a good example of a particular data type and object classification, for example, a specific vendor composite log or seismic acquisition survey. With these templates identified and where a model is generated, we can load a batch of unclassified documents, apply the model to the documents and assign classification. We can then review the results and decide whether we need to update and refresh the model before loading the next batch of unclassified documents, and so on until the model meets your goals and all the files are loaded. What can iterative visualization look like? There are a number of visualization tools available. We use our records management dashboard, which can be customized to present data in a variety of ways. The dashboard can be used to track the evolution of the data as it is loaded and catalogued into our system. The unstructured but now catalogued data can be associated with the structured or digital well or seismic data. It is also possible to use the various filters on the left to visualize what could potentially be millions of files by basin, field, source, or any other tag that has been captured. The geoscientist or engineer will now be able to write a more prescriptive search and locate, open the relevant structured and unstructured data. We'll now look at a use case. We have gained a lot of real-world experience working on subsurface transformation programs, and the intention here is to give some insights into the data we have discovered, the outputs and lessons learned. One operator could see the value in digitalization and realize that a key to a successful digitalization program is about understanding what data they already have in a smarter and more automated way. The main objectives for their project was on improving the data discovery and data quality. For data discovery, they have done some brief studies which found data located in the wrong filing systems as well as many duplicated files. They could also not see which files related to which wells or seismic survey. They wanted to know what data they currently have, what is obsolete or duplicated, and what was of high value. For data quality, their brief studies had shown that they lacked tags and metadata for their project work to be able to determine the quality. Coupled with this, they wanted a better understanding of the documents, underlying the structured subsurface data that could be used to evaluate and then improve data quality. A search of the structured data found that there were 12,000 projects, and analysis of the data allowed for 25% of the projects to be deleted because they were duplicates, 55% to be archived, 18% to be queued for archive at a later date, leaving 2% that were active. In terms of application type, we observed that 45% were from Petrel, 30% were from Techlog, 15% from Paleoscan, and 10% were from Hampson Russell. Understanding the data that was on the systems enabled data managers to declutter and prioritize online projects. This led to a significant reduction in disk space used by old projects, especially Petrel. The intelligent search process that was carried out on the unstructured data took less than 10 minutes to load 1.2 million records. Initially, there was a large number of unknown documents and only a few subcategories when using the standard naming convention, but this was refined as the process worked through the data files. We found that OCR could be slow, taking 10 to 15 minutes on some scanned PDFs. And there were almost 300,000 duplicate files in user areas which could be removed. And standardizing taxonomy within an organization to aid classification and categorization is important. A record of all wells present in each application project was captured, and the data was loaded into a well master database. It was then possible to associate the unstructured data with the well data, and in this project it was agreed that linking the documents to the structured data using the information in the file path and file name was acceptable. Where we're able to display data on a map, a well can be selected from an option menu, and the link to the RM catalogue can be selected. The related records associated with that well can then be listed, and the user or data manager can use preferred tools to open and read the information and decide how to use it. A user can view the associated documents when selecting wells, and they can access the records management module and look at wells or seismic that have been linked to documents. In PPDM, we can leverage the use of data management standards, quality and confidence rules, and the audit tools to support the effective ongoing management of the data record so that it can continue to better serve the end user. And that's the end of our short talk. Thank you very much for your time.